So we're in section 6.2, and we're going to talk about figures, figures in space, and polyhedrons. So let's start with we'll talk about polyhedrons first, but let's remember during first semester, and we did some area formulas with them in our last unit. But let's remember what a polygon is. When we talk about a polygon, what are we talking about? A shape? A shape with a bunch of sides. Okay? That's a perfect definition. So it's a shape with, we'll just say, many sides. And it has to have at least three, because without three sides, it really doesn't make a shape. So a polygon is a shape with a bunch of sides. We talked about a lot of different kinds of polygons. We talked about special polygons, parallelograms, rhombuses, rectangles. And then last chapter we figured out how to find the area of polygons. So in space, in 3 dimensions, we are going to talk about polyhedrons. So if a polygon is a shape with a bunch of sides, what would you guess a polyhedron is? A shape with not a lot of sides? Well, let's think we're certain amount of sides. Let's go back to polygons. Are polygons flat? There we go. 3-dimensional shape with. It has to do with planes, yes. So it has more than one planes. So we have a 3-dimensional shape with a bunch of sides, and the sides are all in different planes. So we just really quickly, we've narrowed it down. So this is a 3D shape with many sides. And we'll give some things some names in just a minute. So a polyhedron is a 3D shape with many sides. The polyhedron has some different properties. So we said that the sides are in different planes. So it's not flat. A polyhedron is not flat. The sides are polygons. So we make up a 3-dimensional shape out of a bunch of polygons. We put them all together, and they're in different planes, and that's how we get our shape. So our sides are polygons. We call the sides faces. So rather than sides, we call them faces. And our faces meet at edges. And the corners, just like with polygons, we call the corners vertices. So let me get a polygon here, and we'll label some sides. So here we go, and we'll label our parts here. So this is a polygon, or I'm sorry, a polyhedron. It's a 3D shape with many sides. The triangles are faces. This is an edge. And the corner is a vertex. So there's an example of a polyhedron. And we'll get into more specific polyhedrons a little later in the unit, and we'll figure out how to find the surface area and volume of our different polyhedrons. When we talked about polygons, what did we mean when we said a polygon was a regular polygon? Anybody remember what a regular polygon meant? What did that tell us about the sides? Sam? They're all congruent. And the angles? All congruent as well. So a regular polygon, all the sides and all the angles are the same. A regular polyhedron is similar. A regular polyhedron has congruent polygons as faces. And the same number of polygons meet at each vertex. So this pyramid, if all of our triangles that make up the faces, if all those triangles were congruent, this pyramid would be a regular polygon. We have 1, 2, and then back here we have 3. So we have 3 polygons meeting at each vertex. So this could be an example, if all of our triangles were congruent, of a regular polyhedron. A cube is another example of a regular polyhedron, because all of our faces are congruent squares, and the same number of faces meet at each corner of our cube. So that's what we mean when we say a regular polyhedron, is that our faces are congruent and the same number meet at each edge. So like a soccer ball is made up of different polygons. We have squares and is it hexagons? Squares and hexagons. So that would not be a regular polyhedron because we have different shapes that make it up. But it would be a polyhedron because we have a bunch of different polygons as faces. But it wouldn't be a regular polyhedron. All right, any questions before we go on? And we'll talk more about these things as we go on in the unit. All right. So our main interest today is lines and planes in space. And we want to figure out how they're related to each other. So when they're parallel, when they're perpendicular, and how we tell. So let's talk about parallel planes. When do you think two planes would be parallel? What would have to happen? Something's laying on top of something else? Okay. What did we say about, so we're getting there. What did we say about parallel lines in our opener? What was important about them? They never touch. So what would we suspect about parallel planes? They never touch. That's how we define a parallel plane. They never intersect. So if we think of the ceiling as a plane and we think of the floor as a plane, those two planes would be parallel because they never intersect. If our ceiling and our floor intersected, we'd be in a building that wasn't rectangular. So our planes never intersect. And if we want to draw a picture of parallel planes, here's one plane. And here's my other plane. Kind of like what Ryan was saying. They never touch. Whoops. So they're kind of on top of each other, but they never touch. And I'm going to make this one look a little better. So these would be parallel planes. They go on forever and they never touch. So how about a line perpendicular to a plane? How would we figure out when a line is perpendicular to a plane? What do you think we'd have to? What do you think would have to happen? What's that? They'd have to touch. So that's one thing. They have to intersect. And what's special about the intersection of things that are perpendicular? 90-degree angle. How could we guarantee that a line made a 90-degree angle with a plane?
There has to be another line on that plane.
So Sean says there's another line on the plane. So it has to do with another line. Now here's where we have to be careful. Let me draw a picture up here on the board. So here's my line, and I'm going to use these markers linked together. This is my other line. So the line made by my markers makes a 90-degree angle with the line that's in the plane of the board. Are the markers, the line through the markers, is that make a 90-degree angle with the plane? No. We need it to face this way to make a 90-degree angle with the plane. Anybody have an idea what we could do with this to make sure that it makes a 90-degree angle with the plane? How about if I drew another line that intersected the first line? And I say that the line through my markers has to make a 90-degree angle with both of those lines. Would that guarantee that it's perpendicular to the plane? Yes. So that's what we have to do. That's how we guarantee that a line is perpendicular to the plane. It has to be, line is perpendicular to every line in the plane where they intersect. And we'll draw a picture so that it makes a little more sense. So here's our Here's our plane. And here's the line that we're interested in, the red one. It needs to be perpendicular to every line that goes through that point where it touches the plane. So it makes a 90-degree angle with this line, and it makes a 90-degree angle with that line also. And with every line that goes through this point. So it has to make a 90-degree angle with every line in the plane where the lines intersect. That's how we guarantee that a line is perpendicular to a plane. Any questions on that so far? So part of what we're trying to do here is get used to visualizing these things in space rather than thinking on a flat surface. So let's talk about a couple more things, and then we'll be done for today. We want to figure out when a line parallel to a plane. So what would we have to have happen to have a line parallel to a plane? So when our two planes were parallel, what happened with those two planes? They never intersected. So we know that our line and our plane have to never intersect. How can we guarantee that our line and our plane never intersect? Anybody have an idea? We have to make sure they never touch, but we want to figure out how we go about that. So when we worked on our opener, we decided that if two lines had the same slope, that they were parallel, right? So can we really find the slope of a plane to compare the one line to? So we could put our lines in all kinds of different ways. But what could we compare a line? What could we compare our line to? An edge. So you're close. Our plane extends infinitely in all directions, right? So how could we make something like an edge in a plane? What would be like an edge? A line. So if we have a line in our plane, and the line that we're interested in is parallel to that line in the plane, would it then ever touch the plane? So if my line of markers here is out here above the plane of the board, and it's parallel to this line that I've drawn on the board, is it going to be parallel to the plane? Because if it goes this way, it's eventually going to hit the plane. It's eventually going to hit that line. So if my line out here above the plane is parallel to a line in the plane, that will make sure that my line is parallel to the plane. So that's how we guarantee that a line is parallel to a plane when the line is parallel to a line in the plane. And we'll draw a picture. Here's my plane. Here's my line in the plane. And here's the line that we're interested in. And the blue line is parallel to the red line. So the blue line is parallel to the plane. That guarantees that this line and this plane are never going to touch if the two lines are parallel. The red line is in the plane, and the blue line is parallel to that line. Can two lines in space never intersect and not be parallel?
Well, yes.
Sean says yes. How would they have to be situated?
Because if one plane's down here, the other one's up here, and they're still parallel. I mean, they wouldn't be on the same plane. Yeah.
So they wouldn't be on the same plane. So the lines can't be on the same plane. So what about their directions?
They have to be like,
They have to go in different directions, right? So we call two lines that are not, so it is possible to have two lines in space that are not parallel and not intersect. We call those kinds of lines skew lines. Skew lines are not parallel and never intersect. So an example of a skew line, if we drew a line down the main hallway up here outside of C wing, and we drew a line downstairs in the C wing hallway, those two lines would never touch because one's up here and one's down here, but they would not be parallel because they go in different directions. So skew lines are, the name for those kinds of lines are skew lines. They're not parallel and they never intersect. So that'll come up a little bit in this unit. And there's one last term that we need to know. The dihedral angle. The dihedral angle just means an angle between planes. So di means two, hedron is our sides or our faces. So this is the angle between two faces of a polyhedron. So it's the way we think of it is the angle between two planes. If we think of this front wall being a plane and the side wall being a plane, what would be the dihedral angle between those two walls? 90 degrees. So dihedral angle just means what's the angle between two planes. That's all that term means. So when you see it, you know what it's talking about. Any questions about what we talked about today? Okay.